Hey everyone, we are going to start the next unit, which is, where is it? There it is, section 12.4, which is applications of indefinite integrals. So let me remind you from the last video, and the one before, that if I take the integral of f prime of x, the integral is the antiderivative. It undoes the derivative, and you end up with the function again. Oops, plus an integration constant. We can't forget the integration constant, of course. And so if I have something like the marginal revenue, which, as you recall, the marginal revenue is the derivative of the revenue function. If I take the integral of the marginal revenue, that will be the same as taking the integral of the derivative of the revenue function, which, as you see from up here, will give us the revenue function plus an integration constant. Now these, for business applications, these can be sometimes easy to find. For example, the integration constant here. If I sell 0 units, how much revenue should I get? Yeah, I should get 0. So if I plug in 0 for X, I need to come out with 0 for the whole thing. So it's pretty easy to solve for C. Typically C is 0. Not always, but usually it's 0. But it's important that when we sell 0 things, we get 0 revenue. So here's an example. We have a marginal cost function of 3x plus 50. And we want to figure out what the total cost is, the total cost function. So I'm going to integrate 3x plus 50 dx. So this is going to be x to the first power. So this will be 3 times x squared over 2 plus 50. This is x to the 0 power next to it. So that'd be x to the 0 plus 1 over 0 plus 1 plus c. And we're also told in this example that the startup cost, the cost when we've sold 0 things, is 10,000. So this is the flat rate cost to just turn on the machines. So that's setup cost and everything. And something like in printing businesses, this is expensive because you got to set up all your dies and your punches and all everything. In the case of companies retooling right now to make ventilators, this is a huge number because you have to redesign some of your equipment to make ventilators. And so the startup cost, the setup cost is big. So let's see. So if I take my cost function over here and I plug in 0, so 3 halves times 0 squared plus 50 times 0, oops, that's a 0, plus c, that should equal 10,000. In this case, we know c comes out to be 10,000. So my cost function is, oops, that's a crummy equals 3 halves x squared plus 50x plus 10,000. Now, if I want to do something where I want to minimize the cost, how many units do I have to sell to minimize the cost? Or what would the average cost be? Average cost, if you remember, average cost is the cost function over the number of units. Now I have a cost function here. So I could use that and stick it in here to figure that out. Or if I was going to do the profit, now I know the cost function. So I'm able to plug it into here and optimize the profit. But let's do something for fun, and I promise this will be fun. Let's take the derivative of the cost function. Oh, that would be fun. Okay, so it's 3/2 times the 2 comes out front, x plus 50. That becomes 0. Oh, look, the 2's cancel. We ended up with 3x plus 50. Look at that. That is the same as our marginal cost function we started with. So I did the integral, the antiderivative, and got the function. Then I did the derivative, and I went back to where we started from again. The integral is the antiderivative. It can undo the derivative. Okay, let's do another problem. Okay, so this is example 2 in the text. The marginal cost is equal to 3 times 2x plus 25 to the 1/2. I bet it probably said 3 times 2x plus 25, right? Probably said that, but I'm just used to getting rid of radicals and making them exponents. And the question asks, what is c of x? Okay, so I have a derivative. I can integrate it to get the original function. So I'm going to take the integral of the marginal cost function. So it's the integral of 3 times 2x plus 25 to the 1/2 dx. Uh-oh, this one's not a nice, easy polynomial where I can do the x to the n plus 1 over x to the n plus 1, because I got this 1/2 here. I have a function raised to a power. This looks like integral of u times du. So I need to do my thing here. Let u equal the thing that's raised to a power, 2x plus 25. So du would be, derivative of that is 2 times dx. Do I have a 2 dx? No, I just have a dx. But I can multiply by 2 and divide by 2. So now I have 1/2. And I'm going to move the 3 out front because we don't really need it. We only need the 2. So 2 times 2x plus 25 to the 1/2 dx. So now I have my 2 dx. So now I have, this is 3/2. So now I have u to the 1/2 du. And we know that's going to be, let's see, 1/2 plus 2/2, 3/2. Okay. So this is u to the 3/2 over 3/2. And the 3/2 flips and becomes a 2/3. Cancel, 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 cancel. Yay. So this is, I'll plug back in for u is, where's u? Right here, 2x plus 25. Now to find the integration constant, c, we need to know some more information, like what is the setup cost? What is the flat rate cost? What is the cost to just turn the machines on? And in this case, the problem tells us that the cost when we have made nothing is $11,125. So I'm going to plug 0 into my cost function. So it's 2 times 0, oops, plus 25 to the 3/2 plus c. And so this becomes 0 plus 25 to the 3/2 25 to the 3/2 is 125. And all of that, we're told, equals 11,125. So if I solve for C, C has to be 11,000. Oops. So that's what we're going to plug into the integration constant in order to write our total cost function. Does that make sense? I bet it does. Let's do one more. Oh no, this is a long one, so we'll break it here and we'll do the next one in a minute. Okay, bye-bye.